if you can look into dog bone specimens, the case study that we have, right? So assuming, okay, if you still remember, our force previously is applied on tops. So how if I change my force applied at here, boundary at here, the mesh I'm still using the same. Okay, so the deformation will be, of course, like that lah. If you see that the deformation due to a static pressures, okay, applied on this surface in what z directions with the 500 Pascal fixed support at the bottom, so it will deform like this. Okay, clear? The stress that induced due to this static pressures, 500 Pascal itself, is around 4.7. Okay, so if you remember, under failure analysis, we try to call out the stress to, we find the static failures factor of safety, right? So we found that it's above 15, all are 15. So basically are all very safe, 15 and above, no issue at all. So no static failure will happen if you apply 500 Pascal on this particular surface. So these deformations creating this, inducing this stress will not cause any static failures. All right. So in the fatigue analysis, if you still remember, we are assuming this equivalent stress that caused by this static pressure of 500 Pascal, okay, which is 4.71, now become completely reversed. Right? So under fatigue analysis, we put a factor of 1. So we are assuming that this static pressure of 500 Pascal will induce a dynamic stress of 4.7, negative 4.7, 4.7, negative 4.7, right? So in this case, if we go through fatigue analysis, the factor of safety also show 15 and above, no issues. Okay, the life, of course, is infinite life, right? Because you have no issue with fatigues, then you have an infinite life, right? So in this case, we are not considering, you are considering the pressure, okay, dynamics pressure, but we didn't really look into its frequencies, right? What is the frequency of this? Right? What is the frequency of this dynamic stress? No. So we are assuming the amplitude itself now is completely reversed. What will be my fatigues? Okay, so it is good, infinite life, right? But if we go a little bit detail on dynamic analysis, so if we go towards model itself, right? So we have a free vibration under model, we have a fixed, then free vibration, no force. So we get our modes, first time modes. So we see that our first mode is like this at 356.31. Then we have at this, the second mode at 1907. Third mode, okay, in the X directions. Fourth mode, in the bending, the second bending mode. All right, so these are it will happen at 2774. So this is the dynamic behaviors at different frequencies. We know that how it will behave. All right, so if we look into, if we take into consideration the dynamic behavior of this particular so-called dog bone specimen itself, okay, to determine our displacements. So here we combine with a harmonic response with this model and model analysis. So in this setting, if I'm looking at the frequency response from 300 to 400, we want to see the effect of first mode at 356 itself. So if we look into this 300 to 400, then solution interval is hundreds, then we are having the data point of 301, 302, 303 until 399, then 400, right? 100 data point. Okay, so if we solve this with the same pressures, 500 Pascal onto the same surface itself, right? So you can see the effect of frequencies, okay? From 300 itself, because it's still far away from its first natural frequency at 356, right? So you have a displacement or deformation at around 3 power of -2 meter mm. Okay, but when it go near to 356 itself, it can go up to 5 mm. Okay, a lot, right? A lot, right? The difference. So the effect of frequency, okay, the effect of frequency on the amplitude is there. Okay, if you have considered this, so it can go up to from 3 power of -2 mm to 3 to almost 5 mm amplitudes. Okay, harmonic response in this case. So if you look into the total deformations, so the 356 hertz, right? So it's actually vibrating or deforming like this, okay? At around the total, at total deformations, at around 13 mm, okay? It's a lot, right? It's a lot, 13 mm. This 13 mm, if this is vibrating at 13 mm, so the equivalent stress that induced is actually 2,700. Okay, megapascal. Can you see that? So the effect of frequency is that. So if you, unfortunately, you run this, you excite this so-called the specimen itself under a harmonic excitation at the frequency of 356 hertz, right? It is very close to, or it's coincide with its first natural frequency at 356 hertz, 356.31 hertz. Then it will generate very high vibrations, 13 maximum at 13 mm, and very high dynamic stress at around 2,700. Right, so that is what it means. All right, do you get me? Right, so if that is the case, right, 2,700 compared with what you have just now, you consider this is just 4.71 megapascal compared to 2,700. So it's around how many times? 500, around 570 times. Right? So if you can revisit this fatigue analysis again, so you can scale it to 570 times. This completely reverse 570 times of your equivalent stress of 4.7 itself. Then you can find out that the sensitivity factor is no longer more than 15. Okay, it's only 0.03. Okay, so this will happen, the failure will happen if you run, this thing is only valid when you excite your specimen with the harmonic excitation at a frequency of 356, right? 356 hertz, right? So the stress is 2,700. So it's 570 times larger than this 4.7 originally. So if you do that, the safety factor is below 1, is far below 1, is only 0.03. Of course, static failure will happen, and you have to predict the finite life. The finite life is only 22 cycles. See that? After 22 cycles, this thing will fracture. Okay, so that is what it means. Okay, so if you consider the effect of frequency, it comes earlier than what you have expected. Okay, so you have to consider, if you are talking about dynamics analysis, fatigue analysis, then you have to consider the effect of the frequencies. Okay, so in the case of, let's say, I'm not going to excite this thing at very high frequency, maybe just 100 hertz. Okay, so 100 hertz itself probably no issues, or maybe I will just run 100 hertz, right? So in this case, or maybe 10 hertz. Okay, I've just run at 10 hertz, excite at 10 hertz. Okay, excitation frequency 10 hertz. The force still the same, the amplitude the same, still 500 pascal. But the frequency, that maximum that I can go is just 10 hertz. I'm not going to 356, right? So in this case, your analysis, if you can go towards, let's say, 10 to 20, probably. So if you have 10 here, so I probably here I want to go for 10 hertz only, 10 hertz only, okay, then we would want to see the stress induced at 10 hertz. What will be that? Okay, so if you can solve it, so you have to wait for a while. We have 10 data points to solve. Okay, so you can have a look on the stress. So 356 hertz, because it's near to the natural frequency, so you will induce very high vibrations, high deformation, and high stress. So this high stress can, if you consider that, if you run this specimen at 356 hertz, the stress induced is 570 times larger than if you consider it as statics. So the fatigue will happen far more earlier, okay, only 22 cycles. But if I'm running at 10 hertz, okay, so you have to rerun again and see at 10 hertz what is the deformation, what is the stress that you induce, okay, due to these deformations. So if you look into this at 10 hertz, at 10 hertz, I'm putting 11 hertz, okay, it's at 11 hertz. So this 11 hertz, the stress is only 4.71, right? So it's not so so much different between this 4.71 and your statics, because the stress, the effect of frequency is very far away, because the first natural frequency is at 300. 300 is very, the 10 or 11 hertz is very, very far away from this 300. The contribution from the first mode or other modes coming into play is very, very less significant. Okay, so it's around 4.71. Okay, so it's similar with this. Okay, 4.71 megapascal. Okay, so in this case, this safety factor is still valid. Okay, at 11 hertz, no issues. Okay, no fatigue. But in the case of talking about at its first natural frequency, okay, if it's running at its first natural frequency, then you will have failures, and it comes much earlier than you expect. That's 22 cycle, this whole thing will break. All right, so that is thing that I would want to highlight and would want you to consider, okay, in your so-called fatigue analysis. Okay, so we think that this is a more appropriate if you take into consideration of the effect of frequencies.